So we're going to start to think about landscape features, in particular, the geology and the geography and what that says about the diversity that we experience here in California. So this is a shot from the Marin Headlands, where one of my field sites is, and we're looking down towards San Francisco. And what you're actually seeing here is just in that foreground and then or midground and then background, you're seeing parts of the Pacific plate relative to the North American plate. And so what we're seeing is this incredible, robust and rugged geography, and that is from this slow motion collision between North America and the Pacific plate. And that entire area that rings the Pacific Ocean we refer to as the Ring of Fire. And that Pacific Ring of Fire is essentially governed by all of these plate tectonics that are moving. And as they move, we have North America drifting towards the south at 2.3 centimeters per year, the Pacific drifting upwards at a similar rate. What we're seeing here is this whitish long line that is indicating San Andreas Fault. And just where the San Andreas Fault tips out into the Pacific at Cape Mendocino, that's where the Gorda Plate takes over. And so the Gorda Plate, rather than sliding against the North American plate, is actually pushing into the plate and subducting, which means pushing beneath the North American plate and giving rise to some of the unique geology we see to the east of that area. And of course, even while these plates are moving at only 2.3 centimeters a year, we can at times have these slip strikes, these experiences where things happen that are a little bit more shaky, such as 1906 earthquake that happened in San Francisco, which devastated that area at the time. Also, another product of these motions of the earth are things like tsunamis, such as the 1964 tsunami that struck Crescent City. And of course, we see this legacy in the incredible terrain that we have in California, the Sierra Nevada, that backbone again of our floristic province with their granitic peaks rising up as a result of that collision between North America and the Pacific. Also, we can look to, again, areas where there's that subduction from the Goida Plate leading to volcanism, which form the southern part of the Cascade Range, in this case, Mount Shasta, and then also just to the south, Lassen. And something you can notice just from this picture is that not only does this lead to variety of texture, but also it's going to inform climate. So you can imagine that with that climate elevation, we're going to experience changing in seasonal temperatures. So we may experience variation then in how much moisture is present, maybe how much light exposure we have. We can expect that that snow and glacier pack that exists on Mount Shasta throughout the year will start to melt and provide some nourishment to the dry, parched California landscape during the summer months in the form of rivers and streams that flow off of these and from these snowpacks. And then we can also think about how in those lower lying valley areas, we might see a cooler, moisture environments, largely driven by the fact that these areas are protected from wind flow and also from some of the solar radiation we experience elsewhere. So here's a picture of the Trinity Alps. You can see a really clear division as we face either north or south, what we see growing on that landscape. So you can see that we have a north-facing slope in the distance, a south-facing slope up front. We call this a direction which a slope faces its aspect. And what you find is, just like in your home or office, if you go to the south side of your building here in the Northern Hemisphere, that side is facing towards the sunlight. So the sun tracks throughout the year closest towards the equator. And so that means that throughout the year, even at noontime, the sun is always slightly south of us. And so as a result, south-facing slopes experience more light, more heat. So those south-facing slopes in drier places, such as on a mountainside, they're going to have more of or less vegetation. Those north-facing slopes, it'll be cooler, wetter. We might see more trees growing. So topography plays a big role in what will grow where. But something else that topography and the underlying features that inform that topography, the geology will inform, is also the soils and what we have as a medium for our plants to grow from and the nutrients that are available to those plants. So I want us now to think about soil. And in terms of soil structure, we can break into these three components: sand, silt, and clay. To give you a reference of what these sizes look like, that's what sand looks like in comparison to clay. So clay is very, very small. Sand and silt are both essentially inert materials. So that means if you've ever built a sandcastle, you know that when you add water, you have this nice structure and shape. But as soon as it dries out, the strength of the hydrogen bonds in the water that would have held that castle together, they are lost, and the castle just crumples and takes this kind of lumpy pyramidal shape, right? In contrast, clay has lots of ions, so cations in particular, that help to bind that material together. So they have a certain innate clumpiness, whether or not there's water present. And that's why you can use clay to make adobe structures or to make a coffee cup, right? So clay has this binding property to it. When we have all these different structures together and mixed in various ratios, it creates the soils that we see on our landscape. Sands, for example, because they are larger, because there's going to be more pockets of space between their individual grains, more opportunity for water to move through that air, through the sand, and also for air to exist that can facilitate microbial communities that may be dependent on air. In contrast, something like clay, it will hold on to water a lot better. There's fewer air pockets, and also it's going to do a lot better job holding on to nutrients that may otherwise be flushed out of that system by water, or that may not be able to bond with the ionic properties of the clay. So clay, being ionic, also happens to be particularly acidic. And that can be both positive and negative in terms of what community structures you're looking at, since it can influence how well, again, nutrients are held onto, but can also mean that it can be hard for plants to access those nutrients. What all that looks like when we put together, it gives us a certain soil structure, and I've included as a reference link dichotomous keys, so basically these which way charts that allow you to kind of figure out, based on soil structure properties, what the different concentrations of these soil components are present within the soil you're looking at. When we have even mix of all three of those components, we call it loam, and loam is typically seen as a pretty good growing medium, since it kind of brings together the different attributes of each of those different soil types. But again, different plants will have different proclivities for different soil types. So you'll have that key in your reference resources. We also need to think about color. And so for thinking about soil color, we use something called the Munsell, soil Munsell chart. Munsell originally developed his color theory for graphic design, but it ended up being more popular with scientists. His color theory works on three axes. So first we have to consider what the proportion of different primary colors are present in that color of soil. So for example, in this case, what's called hue 5 would be referring to that little yellow box, one to the right at the top row. And that would be some mix of yellow, cyan, and magenta that would produce that color. And then from there, we decide how value and chroma influence that particular color. So value being essentially adding black into our color, so darkening it. You can think of it almost like casting shade onto that color. And then chroma being how washed out that color is. So you might think of that as if you have a favorite shirt that's a bright color and you throw it into the wash over many times, it starts to lose that color and fade and become closer to white. So that's what chroma and value are speaking to. And then hue is speaking to that specific components of our primary colors. So we can use this then to key out a soil color. So if we had this example of soil that has this kind of yellowish hue, I looked at it and I keyed it out to being what's highlighted in this little blue box, which we would read as 8/4 5y. So I've also included as a resource a online Munsell soil key that you can use if you want to key out the different colors of soils. And there's directions on how best to use that. In some cases, you may want to work with wetted soils as opposed to dry soils. But it's worth noting that your particular monitor may not be in gamut, which means your monitor may not be displaying those colors accurately. So it might be best to either check out from a library or ag commissioner a copy of a physical soil chart if this is something you're really interested in pursuing. So we can then use this to look at all our different types of soils. I collected these soils just in the Marin Headlands in close proximity to that photo I showed you in the first slide. Serpentine, which again is our state rock and has very unique attributes, which we'll talk about in a little bit. A couple of Franciscan soils, which are clay rich. That yellower soil, Franciscan clay 1, is informed by arenite, which is sandstone. The other is informed by radiolarian chert, which has a very reddish color to it. And then also alluvian soils, which are low-lying soils that typically wash off of slopes and build up in valleys and bottomlands. So I keyed out each of these to get a specific Munsell soil color. And then from there, local ag commissioners or USDA. In my case, I'm working on parkland, so the Park Service had both charts that recognize the textural aspects of the soil and also then soil muscle color. And between those two, I could suss out what exact soil type I was working with and looking at, and from there get a sense of the unique nutrient attributes found in that soil. And so here we can see that that serpentine soil, I mentioned before, it's heavy, rich in heavy metals, but it's also apparently low in potassium, nitrogen, and phosphorus. Our clay soils, lots of clay, obviously. Both are iron rich, as it turns out, and then lacking in some other nutrients. Our alluvial soil, also iron rich. But something you can tell just from looking at the color without knowing the specific soil type are seen in those colors. So soils that tend to be redder or yellower, these are soils that are undergoing oxidization in particular of iron. So that means that iron is more available in those rustier colored soils as compared to bluer, grayer soils, which typically have more saturation or less iron present. And that's because essentially they are more basic as opposed to more acidic. So we're seeing less, again, oxidization. And then looking at a soil like an alluvial soil, you can see how it has all of that dark coloration to it. That dark coloration is a product of iron, or excuse me, of organic material. So you can think of carbon and carbonization and how that is leading to those like blacker colors in that soil. And then something else that we can find with lighter colored soils, particularly for nutrients that are easily washed out of systems that are what we call mobile nutrients. And those are things like nitrogen, potassium, and phosphorus. Things that you often have to put as fertilizer to your plants because when you water them, they're getting rinsed out of the soil. When you see soils that are lighter in color, typically those are soils also that have been washed out of many of the essential nutrients. The nutrients that are non-mobile that can stick in the soil, they will stay put. So these are general rules of thumb, but things that you can start to identify when looking at different soil colors. So when we think about soil and rock, this idea goes back many centuries, and in France, in the viticultural industry, it's referred to as terroir, the influence that soil and terrain, in particular geology, will have on the grape and the taste that grape lends to the wine. We can think of that as well in its influence on really any plant. And so I have mentioned in the second lecture, Bacchus pilaris, a plant that's sometimes seen as being invasive in its range. Maybe a better way to characterize it is it's very much a generalist. It can grow in many different soil types. So I want to look at Bacchus and at Bacchus growing on each of these soil types to now think about how we can define soil and the limitations of soil based on what that plant tissue is showing us and the effects in that plant tissue. And in fact, this is a technique that's used on a more rough scale by folks like the USGS survey when determining soil type and rock type by looking at vegetation patterns to determine what the underlying conditions might look like. So here are 4 leaf tissues samples from 4 different Baccharis. You can see at the top one that's got lots of yellowing and this kind of purplish coloration to the new leaves. The second one has also variation in tissue with the younger leaves looking very yellowed and burnt at the edges, whereas those older leaves tend to be kind of green. So that's kind of interesting. Our third example has green young tissue, but then that older tissue appears yellowish. And then that fourth sample, I think looks pretty darn healthy. So I just kind of identified what were some of the traits that I noticed in these. And what I saw again was, those qualities of all the tissues looking burnt and yellowed. What you'll notice is that between 2 and 3, we have 1 in which there's a lot of tissue that's already yellow in the older tissue versus yellower in the younger tissue. Before I mentioned mobility of nutrients, so I want to go back to that real quick. When we're talking about nutrients that are mobile, they're mobile not just in soil, but also in plant tissue. So if a plant is trying to invest in new growth and it has a limitation of a mobile nutrient like nitrogen, it can allocate those nutrients from the older tissue into the newer tissue. So that might be what we're seeing in figure 3, where that greener tissue is that younger tissue. In contrast, looking at number 2, where we see tissue that is more yellow and burnt in our younger tissue, but greener in our older tissue, it could be instead that what we're seeing here is an issue of an immobile nutrient where we're not able to reallocate a limiting resource from older tissue into younger tissue. So let's see so we can take charts that are provided by, in this case, I used a Sunset Magazine book called Western Gardening that kind of gave a sense of what these different leaf colors would tell us about nutrient limitations. But really, there's lots of resources that exist, and I've included one for this chapter that you can use to follow up if you're interested in maybe taking care of your house plants and making sure they get the nutrients they need. But let's see what that chart would have revealed to us. And what we can see is that, again, those really spotty tissues speak to a whole swath of nutrient limitations. And we can see that for number 3, those mobile nutrients are what's limiting, in the sense that that younger tissue has more of those mobile nutrients, whereas that older tissue is now deprived of nitrogen and potassium. And then for number 2, we can also see that immobile nutrients like manganese and zinc, they appear to be lacking, and that's why our younger tissue is looking in such ill repair. You can also notice that there's some burnt blackish tissue as well. I don't know if that's a symptom of nutrient limitation. That could also be something that is parasite driven, but worth noting that oftentimes when there's nutrient limitation, and the impact that it has on the health of a plant will also then impact what you open that plant up to in terms of disease and other implications. So let's match these now to our soil types. And you can see that, lo and behold, that really ratty looking Baccharis, it was growing on that serpentine soil, rich in heavy metals, lacking in many nutrients. And we can again see that our alluvial soil, which was rich in nutrients, rich in organic matter, had the really good looking plant tissue. And again, to recall what we saw as lacking in those soil types, really matches up what we saw in our leaf tissue. So this allows us to kind of think about our system both from the vantage of soil, but then also from the tissue, and make extrapolations about soil based on what we see in our tissue. And so something that, to return to our invasive species conversation, that comes up is that many plants that can be ecosystem engineers, like Fabaceae, in this case, Scotch broom, they can really adapt the landscape by changing soil chemistry. And so here, there's enrichment of nitrogen within the soil. And while nitrogen is often limiting in many of our native habitats here in California, having more nitrogen does not necessarily mean that our natives will do better. And that goes to this idea known as R star theory that was developed by a fellow by the name of Tillman. And what Tillman noticed was that whenever there's a resource that's been depleted to a certain stable state, so as an input and output are consistent, what we find is that the species that can most utilize that limited resource is a species that will thrive and will make its home in that area. So when we have low nitrogen environments, for example, native species may benefit. And native and invasive species may not be able to colonize those spaces as readily and may cede territory back to native species. But as soon as we have, either through an ecosystem engineer or maybe an agricultural practice that leads to more nitrogen in that soil, we have opportunity for more invasive species to come in. And then oftentimes those invasive species that we have in California also happen to be annuals, fast growing, so using more nitrogen than they are carbon in a relative sense in order to expedite growth and reproduction. And as a result, we find that when we have more nitrogen, we might see a shift towards non-native dominated systems. So that soil chemistry is really important when thinking about these systems. And we can see that also in how that affects native species interactions with mycorrhizal associations, so fungi that live in the soil that help to connect native plants and other plants with nutrients and with water. Cytosyparia, so that Scotch broom, by putting nitrogen into the soil, can lead to native plants like Douglas fir not forming positive associations to the same degree with their fungi, which means that later in drier periods of time, not only are they not receiving nitrogen from their fungal associates, they may also become water deprived because those fungi help to also connect them with water during the drier parts of the year. And we can also see this with Phalaris aquatica, which is a grassland species, which can also impact nitrogen, not so much by changing the amount of nitrogen available, but by the type of nitrogen available. So we find that Phalaris aquatica associates with bacteria that create bioavailable nitrogen in the form of ammonium, whereas many natives that grow in grassland systems have a preference, particularly in wet grassland systems where Phalaris is common to invade, prefer nitrates instead of ammonium. And so as a result, we see a different type of nitrogen available, which again can impact and affect what species will grow where. So a consideration of soil chemistry and how plants can affect that soil chemistry is really fundamental in how we evaluate and preserve and conserve spaces going forward. And here are all those Munsell charts, soil texture charts, and also a chart for identifying leaf coloration nutrient deficiencies. I'll turn it over to you all for questions.